Assalamu alaikum everyone. Welcome to our demonstration of the digital snake and ladder game. We are Team Whiplash and our members are Ferdoz Hassan Mahabub, Farhan Tahamid, Mohammad Shihab Alam, Mollik Asifuddola, Shahrin Rahman Shanto, Sajid Arifin Prapo, and myself Ishtiaq Parvez. We developed the whole circuit in the schematic sheet of the software Proteus and also built the PCB design. In this video, we will walk you through every module of the integrated circuit design and explain the functionality of each module. At first, Sajid Arifin Prapo will explain some of the modules, and then I will explain rest of the modules, and then I will conclude the video by running through a gameplay demonstration of the digital snake and ladder game with our schematic.
Assalamu alaikum, this is Sajid Arifin Prapo. Let's start the snake ladder game project by explaining the board module first. Here, the board module consists of 16 blocks. Each block contains 4 LEDs. The lower LEDs are actually the player positions indication, the red and the blue LED, and the upper LEDs are actually an indication of the snake and ladder position. The green LEDs, the upper green LEDs, are actually the indication of the snake's head and tail, and the yellow LEDs are indication of the position of ladder's bottom or top. Here to mention, the lower LEDs are actually kept in the active low mode because these LEDs are connected to the output of the player position decoders that has outputs of active low. So these lower LEDs of each blocks are kept in common anode, and the upper LEDs are in the active high mode because these are connected with the outputs of the snake and ladder module that has an output of the XOR gate output, which is active low. So these are kept in common cathode. We have written the numbers on each blocks of the board module so that we can easily determine the position of the snake's head and tail or the ladder's bottom or top from the snake module and ladder module inputs. So let's move on to the next module, that is the snake module and the ladder module. As for the snake module, it is actually for the determination of the snake position in the board module. It takes two inputs, that is the snake head and the snake length, and by these two binary inputs we can determine the snake's tail. How? Let's break through it. Here, the snake head is going directly through a decoder that determines the snake head in the board module, the position of the head in the board module, and for the snake tail, we have to subtract this length of the snake from the head to get the snake tail. For this, we use a subtractor, and these outputs are the snake tail, and that is going through the snake tail decoder, and there is a 16 output of this decoder that are active low. Both decoders have 16 active low outputs, that is a total of 32 outputs, and these outputs are going through a XOR gate. And what is the purpose of these XOR gates? So we know if by any chance the snake head and the snake tail in the same position, and as we know the XOR gates are odd one detector, so the inputs of these XOR gates will be same. So there will be an output of 0, and that is an invalid output, so there the lights will not be shown up as for the snake module. See, if we can look at the board module, that the snake module head is 1100 binary number, that is corresponding of decimal number 12. If we see in the board module in the 12th position, the green LED, that is the snake head, and if we see the snake length, we see that 1010, that is corresponding decimal number of 10. So the snake tail should be in the position of 2 in the board module. So we can see there is a LED, green LED, that indicates the snake tail in the board module. Now let's move on to the next module, that is the ladder module. It is actually same as the snake module. It also takes two inputs, but one is the ladder bottom and other is the ladder length. By these two inputs we can find out the ladder top. How? Let's break through it. Ladder bottom inputs are going directly through the decoder, that is the ladder bottom output decoder. It gives 16 outputs that decodes the position of the ladder bottom, and for the ladder top, the lengths of the ladder are added to the bottom of the ladders by an adder, and these outputs are the ladder top. These outputs are going through the ladder top decoders that decodes the position of the ladder tops. So these 32 outputs are going through the XOR gates, and the XOR gates operation are same as the operation that it was in the snake module. Now, if we consider as specific case that by any chance if the ladder bottom and the ladder length are in such a way that the ladder top exceeds the position 15 in the board module, as we know the maximum position in the board module is 15. So if the ladder module exceeds the 15th position. To eradicate this flaw, we could have used these enable pins of the decoders. How? If the ladder top exceeds the position 15, there will be a carry 1 here, and we could have just connect this carry output to these enable inputs of the decoders. And by this, the enable inputs will be 1, and it actually disables the decoders, as it is these two are the active low decoders. So there will be no LED light up, and it is considered as a invalid case. And for the snake module, we can also dismiss this position by this enable input, but there is an exception. Let's go to the snake module child sheet. This is a subtractor. The carry is already there 1, so we have to connect this carry output to this enable inputs through a NOT gate, so that the enable inputs will be 1 and thus dismiss the decoders.
Assalamu alaikum, this is Ishtiaq Parvez from Team Whiplash. In this video, I'll be explaining each module and how it works, and I'll conclude the video by running through a gameplay demonstration. I'd also like to mention that most of the modules here were kept without subcircuits. It was because we were having some issues due to some bugs. That's why we kept it like this for our debugging convenience. Let's go to the player decoder module. The player decoder module consists of 2 decoders for each player. The IC is 74154 IC, which is an active low. This active low IC is used because it was the only available IC. Now this player decoder takes input from memory module, which will give either the present or updated value. Next, let's go to snake and ladder's logic module. We built this module for some bonus cases also. After completing the explanation of all modules, we will demonstrate those cases. The purpose of this module is to compare snake's head and ladder's bottom with current player's present position and update the position accordingly. Now this module comprises of these few ICs. This is the starting IC. What it does is adds the dice module's value with present player's position. But before that, there is another adder and some AND gates. The purpose of this is to see if the addition value of dice module and the player's present position exceeds 15 or not. If it exceeds 15, then this adder will generate a carry through this NOT gate, which will nullify this AND gate's output. So only 0 will be added to present player's position, so it will stay in the the previous position. Now for all the other cases where the added value doesn't exceed 15, this adder will simply add the dice value with current position, which will come from the memory module. Now the added value will go through 3 segments of comparison, hence 3 comparators are used. In the first segment, the added value will be compared with ladder's bottom, and if the position matches, it will go through this adder, and the output of the comparator will activate the AND gates. Hence, if the position matches with the ladder's bottom, the ladder's length will be added and the player's position will be updated. And then the updated position again goes through another comparator, which will compare the position with snake's head. If the position matches, the snake's length will be subtracted from the updated value. And if it doesn't match, this output, which will give 0, will nullify all these gates, which will subtract only 0. Then the updated position will go through another comparator, and again it will compare with ladder's bottom and add or not add accordingly. Now these 3 segments of comparison enables the logic module to work in 4 conditions. The first condition is where the snake's head and the ladder's bottom is in the same position, so that will work as a priority logic module, so that will only use the ladder. And then the second condition is where snake's tail and ladder's bottom is in the same position, so the current player will go down the snake and then climb up the ladder. And the other another condition is where the snake's head and the ladder's top is in the same position, so the current player will climb up the ladder and then go down the snake. And the fourth condition is a loop where the snake's head and the ladder's top and the snake's tail and the ladder's bottom is in the same position. So in that case, it will prioritize the ladder and climb up the ladder only. I will demonstrate each of the cases after completing the explanation of the other modules. Now we will go to the dice module. Here the dice module consists of 2 operations. One is the asynchronous counter, along with some combinational circuit, which will generate the number from 1 to 3. And for the clock pulse of this asynchronous counter, we are using a 555 timer IC built as per the instruction given in the Google Classroom's lecture video on 555 timer IC. Now this is an isolated version of the dice module. First, I will explain the asynchronous counter. We use 2 JK flip-flops for 2-bit asynchronous counter, and usually 2-bit asynchronous counter generates number from 0 to 3, but we only need numbers from 1 to 3. So we used this NAND gate, the output of which is connected to the reset pins of the JK flip-flops. So if the counter reaches 3, it will reset the counter, so it will set back to 0. So it will only count from 0 to 2. Now then we used these XOR gates. These XOR gates will invert, so rather than 0 to 2, it will count from 3 to 1. So it will act as a down counter, counting from 3 to 1. Now the clock pulse of the LSB comes from the 555 timer IC, and the clock pulse of MSB's JK flip-flop comes from the LSB's output. Now the 555 timer IC was built according to the lecture video given on the Google Classroom. This output pin Q will generate a stable multivibrator output, and this output will be only produced when the VCC pin, meaning the power signal, will be short-circuited with the reset pin. So here we used a push button which will act as a momentary switch. So when we hold the push button, this VCC pin and reset pin will be short-circuited, and at the Q pin the stable multivibrator output will be produced, which will give the clock pulse to this LSB. The values are chosen for a suitable frequency which is very high, which will give us the pseudo-random number generation. Even though it will be down counting, but it will be doing so fast that it will be random, and we cannot possibly choose for our own convenience. Now we can decrease the frequency of the output by increasing the value of this resistance and decreasing the value of this resistance, and also increasing the value of this capacitance. Now by doing this, we will show how the down counting is happening, but slower. Now if we run the circuit, as you can see, if I click once at a time, the down counting is happening, but if I hold it, nothing is happening because of the value of this capacitance is so big. It's not discharging properly. Now if we change it back to the previous value, it will show the down counting is happening slowly. So you can see it's going from 3 to 2 to 1, again to 3. That's how the dice module generates. Now I'll be explaining the memory module. Initially in the phase CDE, the file we submitted had some issue in the memory module. That's why we had to keep the memory module out of the subcircuit. Then finally, before submitting the files including PCB designs, we fixed the issue. Now the main part of the memory module is basically 2 D flip-flop registers, and because the logic module can only flow one player's data at a time, that's why we had to use this marks, this 2 to 1 line marks, for selecting each time the active player's data to go through the logic module. And also, after passing through the logic module, we built a DMUX with subcircuit because we didn't find any proper working IC for DMUX. And this is the child sheet of the DMUX. And the function of this DMUX is to pass through the updated value of the current player's position and making the registers taking that input. And here each group of 4 pins here are indicated for player 1's updated position and player 2's updated position, and these 4 pins each are connected to both of the D flip-flops respectively. One of the 4 pins are for player 1 connected to D flip-flop number 1, and the other is connected to D flip-flop number 2 for holding and updating and holding the current player's updated position. And the reason for the player's updated positions for player decoder is not taken from the DMAX is that while one player is active, DMAX will only flow the updated position of that player, but the other 4 pins will only show 0, 0, 0, and 0. So that will mean while one player is active, that player's updated position will be shown in the board module, but the other player will be shown the position in for the other player, the position will be the 0th square, which is wrong. That's why we took the input for player decoders from the output of D flip-flop. This D flip-flop will immediately update the updated position taken from the DMAX and give the output. After they give the output, each of the decoders will take corresponding 4 bits and show in the board module. So this diagram actually shows accurately how the memory module actually works. The logic module here takes the dice number from dice module and also takes the current player's position, which is activated by the player selector module from the max. And after the logic module updates the position, it goes through the DMAX, and the DMAX sends the current player's position to the corresponding D flip-flop. Let's say for player 1 it sends the data to D flip-flop 1, and after then the D flip-flop gets clock pulse and updates, and then the output goes to player decoder 1 for player 1. But all the while D flip-flop 2 will hold the previous value for player 2's previous position, and so the player decoder 2 will be showing that player's position in the board module all this time. So that's it. That is the workflow for memory module. So that is the workflow for memory module. Now the intricate part of building the memory module was to maintain the clock pulse and maintain and control which input to Now the intricate part of the memory module is to maintain the clock pulse and also control for which D flip-flop the input should be allowed to go into the output, because as I have mentioned earlier, the tricky part of the DMAX is that when one player is active, the output for other players is 0, 0, 0, 0. So for each clock pulse, which will come from the dice module, for each clock pulse, if we allow 2 of the D flip-flops, meaning the registers, to take the input and show it in output, then every time the other player will have stored value which will be 0. That's why we utilized these 2 pins of the registers, which is input activation pin. So these are active low. So if these are if these pins are fed 0, then only the register will be the input will be activated for this register, and the inputs along with the given clock pulse will be shown in the output. Now to understand the signal sources for the clock pulses of registers in the memory module, and also the input activation pin, and also the selection pin in the max and DMAX, we need to first understand the player selection module. So the reset module So the player selection module consists of nothing but a master-slave flip-flop. We know that the primary function of a master-slave flip-flop is to have a toggling output, and the toggling output of the slave flip-flop is connected to the input activation pin, also the max and demax's selection pin. Now we need the signal for input activation and max and demax selection pin to toggle whenever the push button of the dice module is pushed. So every time the push button will be pushed, the output of this slave flip-flop will toggle. Hence, the player activation will change. If previously player 1 was activated, then after again pushing the dice button, the player 2 will be activated, and through the marks and demarks, player 2's updated or present position will be passed through. And in the case of input activation pin, because it is active low, we have connected player 1's register's input activation pin directly with the slave flip-flop's output. We have connected the inverted output of slave flip-flop with player 2's register's input activation, so that each time when the output gives 0, meaning when marks and demarks will pass through the player 1's present or updated position, the deep flip-flop will have activated input and will pass through the input to output whenever clock pulse is given. Now, for the dice module to be connected with player selection module, the clock pulse for the master flip-flop is taken from the inverted signal of this reset pin. So whenever dice is pushed, this power will be short-circuited through this line, and the clock pulse will be generated for the master and slave flip-flops. And here we can see the slave flip-flops clock pulse is directly connected with the reset pin of the 555 timer IC, and the master flip-flops clock pulse is actually connected to the inverted line of the reset pin of the 555 timer IC. The reason for this is we know that the timing diagram for a master slave flip-flop, it looks like this. So the slave flip-flop actually is negative age triggered, and the master flip-flop is actually positive age triggered. But when we actually invert the clock pulse, then the master flip-flop will become the negative age triggered, and the slave flip-flop will be positive age triggered, but it will not be triggered until the master flip-flop has been triggered once. So the slave flip-flop's triggering will go to the next cycle, and thus the timing diagram for player selection module becomes like this. So each time the dice module's button is pushed, the player selection module's output, which is the slave flip-flop's output, is toggled from the second time. At the first time the dice module is pushed, the button is pushed, the player selection module doesn't toggle the output. So it means first time the dice is pushed, the player 1 stays activated because the output stays or remains 0. Now in the memory module, for the clock pulse of each registers, the clock pulse have to be triggered whenever the push button of the dice module is released, because if the clock pulse is triggered the moment the push button is pushed, then the register will take whatever instantaneous value is updated through the logic module, because when the dice button for dice module is pushed, the number is still being generated. So it is better triggered when the dice button for dice module is released. Now even if the clock pulse is triggered at the same moment of the release of the push button in the dice module, there might be some instantaneous changes, and that's why we were facing some issues in the phase CDE. That's why ultimately we had to use a debouncing circuit, and then we came up with this debouncing circuit, which is an RC circuit. The function of this RC circuit is to have a time delay. So whatever value the reset pin is getting, which is the power source whenever the button is pushed, the same signal is also passing through this line, and because of this parallel RC circuit, there is a time delay for each signal. And of course, for making the D flip-flops registers negative age triggered, which is needed for getting the memory module triggered after the release of the button. After we release the button, there is some time lag. Then the registers are triggered and the updated position is updated through the output. And of course, only the activated player's positions gets updated. For the other register, which is inactivated, even though there will be clock pulse, but the output will not be updated because of the inactivation of input pin. The output will stay as the previous position for the inactivated player. And As you can see, we have used a diode here so that the RC circuit might have only one-way functionality. It doesn't function or discharge signal the other way, meaning the reset button or the reset pin. Now the reset module is nothing but a push button and a power signal, and this push button is connected with this reset pin of each registers in the memory module. And because the player decoder's input is taken from the output of memory module, which shows the present or updated position of the inactivated or activated player, whenever this button is pushed, this reset pin gets activated and the output for every registers becomes 0. So the game starts from the beginning again. Now the winner module consists of nothing but two LEDs, a red LED for player 1 and a blue LED for player 2. Whichever player reaches the 15th position first, this the corresponding LED will light up. Now, because the player's position LEDs are common anode because of the active low output of the player decoders, so the winner module's LEDs are also kept active low, meaning common anode, and the cathodes of each of the LEDs are connected to 15th squares player position LEDs, and it's connected to the cathodes of each of the LEDs. So whenever each of these LED lights up first, the winner module's correspondent LED will also light up. Now I will be demonstrating how the logic module works under 4 exceptional conditions. The first condition is priority logic, where the snake's head and the ladder's bottom is in the same position. So we kept the snake's head and the ladder's bottom in the 5th square of the board, and ladder's length is 7 and the snake's length is 2. Now we will start the game to see what the player position does whenever it reaches the position 5. So here the player 2 reached the position 5 before player 1, and rather than going down the snake, it went up the ladder. It means that the priority logic worked. Now we will see the second condition, where the snake's head and the ladder's top is in the same position, as well as the snake's tail and ladder's bottom is in the same position. It means that it becomes like a loop, but here also the priority logic works. Now to get the player's position back to 0, we have to reset the game. So as we see at the first try, player 1 got 2. Now after getting 2, rather than running in a continuous loop, it chose ladder as the priority logic. Now we will see another condition where the snake's tails and ladder's bottom's position is in the same position. In this case, if any of the player reaches snake's head, it will go down the snake. Then after that, at the same time, go up the ladder. Meaning here we put the snake's head in 6 and the snake's tail in 2, and the ladder's bottom is also in 2 and the ladder's top is in 4. So whenever a player reaches 6, it will go back to 4 rather than 2. Now let's reset the game and start again. So after getting 2, player 1 went up to 4. We have to reset again because both of the player went past the number 6. As you can see, from position 4, player 2 got 2 in the dice module. So adding 2 with 4, it gets 6, but reaching position 6, it went back to position 4 because there is a snake here, and after going down the snake from 6 to 2, it went from 2 to 4. It means this condition worked. Now we will see if the logic module works in the fourth condition, where snake's head and ladder's top is in the same position. So if any player reaches ladder's bottom, it will climb up the ladder, then again go down the snake. Now we have to reset the game again. Okay, so after the first player got 3, it went back to 1, and after the second player got 3, it again went to 1, because whenever any of the player got 3, it went from 3 to 5, climbing up the ladder, and then in the 5 it met the snake's head, then went down the snake from 5 to 1, because we put length 4 in the snake, so the snake's tail reaches 1. That's how we can be confirmed that the ladder module actually works for all of the 4 exceptional conditions that we built for. Now I'll be demonstrating a full gameplay of the snake and ladder game with this schematic, and we set the position of snake and ladder so that there is no crossover like the exceptional conditions that we showed for the logic module. Now we will go through the game. The first push of dice module was for player 1, and it got 3, and because there is ladder's bottom at the 3, the player 1 climbed from 3 to 8 because the ladder's length was 5. The next push for dice button gives also 3 for player 2, and it also climbed up the ladder. Player 1 again got 3 and went to 11. Player 2 also again got 3. Player 1 got 1, meaning it faced snake's head at 12, so it had to go down 2 because the snake's length was 10. Player 2 got 2, it means it got past the snake's head. It means that it has nowhere to go back now. Player 1 again got the ladder. Now player 2 got 2 at the position 13, means that it reached the 15, and as the player 2 reached 15 before player 1, it means that player 2 won, and here the winner indicator also shows this. Thus the gameplay is complete.